get started. So we have an exam tomorrow. We've talked about a lot of these problems. What problems do we want to talk about? So we've done a lot of these spherical or cylindrical.
You do a center of mass for a 3D.
Yeah. Triple integral center of mass problem. Let's see if I can find one. Center of mass. That's a two-dimensional one.
Is it going to be a two-dimensional center of mass or a three-dimensional?
I don't know. This one's probably a good one. We should probably do 57. The paraboloid bowl bounded by z equals x squared plus y squared and z equals 36. Let's find its center of mass. I assume it has constant density. So does everyone know what a paraboloid looks like? Yeah, it's like a parabola you rotate around, right? It's a parabola rotated around. So it looks like, yeah, take a parabola and flick it. I like that. It's good. So we get this paraboloid bowl type thing. It looks like that. And then it intersects at z equals 36 and has constant density. So let's just say rho, the constant density is k. Just call it k. That's constant density. So it's solid, it's filled in. And so because of the fact that it's constant density and the symmetry of this, where do we know the center of mass has to lie? It has to lie on the z-axis, right? So the center of mass is going to be, so really we just need to compute z bar. So z bar is some triple integral over d of z dv, I guess technically times the density, times the density, which is, we called k. It could be rho, it doesn't matter. I just don't want to use rho in case we're going to use spherical coordinates. So that's why I call it k. And then we have to divide by the mass, which is the integral of k dv over d. So this is the thing we need to compute, right? X bar and y bar are both going to equal 0. X bar, y bar, both equal 0 by symmetry. Okay, so we're in position to kind of knock this thing out. So let's, what kind of coordinate system will be helpful here? Because of this. Cylindrical, right? Because we have x squared plus y squared. So it's z equals r squared is going to be our equation. And so if we were just, for instance, to do the mass, so m was the mass, and we're going to do the triple integral over this guy of k, and then we're going to do it in kind of, I guess we have to figure out what the projection of this is, right? We have to find out what the projection of this guy is in the xy plane. So this is the region R. What is R going to be? It's going to be a circle. And how do we figure out what the radius of that circle is?
Well, because we know that r squared equals z, and then z or 36 is equal to r squared.
Yeah, so 36 is equal to r squared. And so we set them equal to each other. So set z equals 36 equal to r squared. So then r equals 6. So it's a radius of circle radius 6. And so this is 6, 6. That's our region R. So how do we integrate that? If we slice up that region R, that's going to go from James. How do we slice that in polar coordinates? So theta goes from where to where? From 0 to 2 pi. Where's R going to go from? 0 to 6. And now where is Z going to go from? What's our bounding functions? R squared is the bottom one, right? Because it's the paraboloid. And then it ends at 36. 36. And then it's going to be r dz dr d theta, right? That's going to be our mass. And so the k just pulls out. So the k is out at the end. Also, 2 pi will just be at the end too. And then, so this is going to be equal to the integral from 0 to 6. And then if you integrate this with respect to z, it's just z, right? It's just z. And so it becomes 36 minus r squared. So it's 36 minus r squared times r dr, because I already integrated with respect to theta. Is that okay that I skipped that, right? Because it's just the integral of with respect to z is just z, and so it's 36 minus r squared. And then from there, then what can we do? Just do it. Yeah. So it's k 2 pi. So 2 pi k times this becomes 36r squared over 2 minus r to the 4th over 4, evaluated from 0 to 6, I believe. That looks right. And whatever the heck that is, that's some number. 2 pi k times plugging in 36, we get 36. It's actually 36 squared. Fun. 36 squared over 2 minus also 36 squared over 4. That's funny. Over 4. And yeah. So I should pull out 36 squared. Whatever. No, no, no. Just leave it like that. That's the mass. That's the mass. I need to add a page to get the. So that's how we get the mass. What's going to be the difference to get the moment is you do the exact same thing, but instead of integrating k, we're going to integrate zk, right? That's the difference. And so to get the moment with respect to the y, xy plane, I guess, technically is. Sorry. This is going to be the triple integral. So 0 to 2 pi, 0 to 6, and then still r squared to 36. But now it's going to be k z r dz dr. That's a lot of letters. That's actually very confusing. That's kind of confusing. K is a constant, and then r is a constant with respect to z when we integrate. And then you can also multiply by 2 pi, and so it's not much different, but we're going to get a 2 pi k at the outside. So actually, that's going to cancel with that when I compute the z bar or whatever. And then it's the integral from 0 to 6. What's the antiderivative of z now? Z squared over 2 evaluated from r squared to 36. And so we have to plug that in times r dr. So this is going to equal 2 pi k times 36 squared over 2. So integral from 0 to 6. 36 squared over 2 minus r to the 4th over 2 times r dr. This is going to be some disgusting number, but it will be 36 squared over 2r squared over 4, I guess. Let's take the antiderivative. 4 minus r to the 5th over 10 times 2 pi k evaluated from 0 to 6. Oh, buckets, that's a big number. Yeah. It's going to be a very large number. 2 pi k times 36 squared times 36 squared, just a ginormous number, over 4 minus, I'm just going to say 6 to the 5th over 10. I have no idea what that is. But the final answer then, z bar, is equal to, you take this number and divide by that number, which probably simplifies rather nicely. I'm just not going to do it, but it probably simplifies nicely.
36 squared times 36 squared, or just
It's 36 squared times 36. You're right. Not
36 cubed.
36 cubed, which is actually 6 to the 6th. So I could write this as 6 to the 6th, maybe. Not that that will help us, but maybe. So z bar is going to be the moment, which is this number, 2 pi k times 6 to the 6th over 4 minus 6 to the 5th over 10, divided by the mass, which we just computed, which is 2 pi k times 6 to the 4th over 2 minus 6 to the 4th over 4. So actually, I think this is going to simplify actually kind of nicely. So I kind of want to finish it. This is the right answer. That's totally fine. But I kind of want to simplify it. So that cancels, that cancels. The 6 to the 4th on the bottom cancels up top. And we get what's left is a 36 minus a 6. So it's going to be 36 over 4 minus 6 over 10 divided by 1/2 minus 1/4. I think that all cancels pretty nicely. And that actually is not bad. That's 9 minus 0.6. So 9 minus 0.6 divided by 1/2 minus a 4th, which is a 4th, divided by 0.25. So whatever the heck that is. 8.4 times 4. Whatever 8.4 times 4 is, just 32 plus 1.6, so 33.6. So the center of mass, that's kind of interesting, right? The center of mass, the thing only went to 36. And the center of mass is almost all the way at the top. That's kind of crazy. That seems wrong. That seems way too high, right? Doesn't it seem way too high? Well, it's constant density. It's a paraboloid. And so is there really that much mass above it as below? That seems kind of bonkers. What did I get before when I did it? Let's see. Yeah, I mean, but I could have made so many errors in doing that. Oh, I don't even try. I just leave it. I don't even attempt to integrate it. That's pretty funny. Whatever I tell you in the exam. So maybe you'll have to go all the way, maybe you won't. Just depends. So if it says to set up, then set it up. If it says to finish, you have to finish. But finishing is a number. So that like this is a number. That's fine. That is a number. This was just kind of for fun. Huh. That seems really high for me. Did I do this? I mean, I might have messed up here. 36 over 4 minus 6 over 10. I agree on that. So that's 9 minus 0.6 divided by 0.4. If you divide by 0.25, that's the same thing as multiplying by 4. So I think it's 8.4 times 4, which is 33.6. I don't know. It seems high for me. What's up, Colby?
How did you just cancel a bunch of this?
Yeah, so the 6 to the 4th here, 6 to the 4th here, I can pull it out, and the 6 to the 4th I pull out here, and it's left to 6.
The K is row?
Huh?
Is the K like?
K is just row. I just didn't want to use row in case I wanted to use spherical coordinates. I didn't use spherical coordinates, but I wanted to reserve row for that letter. So I used K as the density.
Yeah. Right.
It's just a constant though. It is just a constant. And so that's nice. The nice thing when you're computing a center of mass calculation, if the density is constant, it's always going to cancel out of the top and the bottom. So it doesn't, you don't care. Yeah. If it doesn't cancel, you messed up. Exactly. Yeah. We could just put 1 if we want to, but it says constant density, and so technically, if you want, like for instance, if we wanted to compute the mass, it wouldn't just be 1; it would have to be k, because like the mass, it does depend on the density.
The density is greater than 1.
So like if I gave you the density was like 15, then the answer would be 30 pi times whatever this is, which so it doesn't say that the density is 1; it says the density is constant. And so, but when calculating z bar, which is the coordinate, it doesn't matter. It could be 1. But if you need the mass, just the mass, it doesn't cancel. Huh? Okay. What else should we do? You have a particular one you'd like to do?
Close to 100. There's kind of like same different multi exam. The answer book says it's 24.
24. Oh shoot. What did I do wrong? Where did I go? 24. 24 seems much more reasonable. Because about 2/3. Yeah, that makes sense. No, it's not. It's not right though. So what did I do wrong? Guys, help me where I went wrong. There's so many places I could go wrong. Boop, boop, boop. One half minus a fourth, I believe, is 1/4. I'm pretty convinced that the bottom is 1/4 when you like cancel out 2 pi k. And then plugging in 6. Oh, wait. No, that's 6 to the 4th times 6 squared. I believe that's 6 to the 6th. And it should be 6 to the 5th. I don't know. Who cares? Yeah, don't simplify. If you make small algebra errors like that, like arithmetic errors, I don't really care. So let's just ignore this. Okay. What else should we do? So you want to do a switching of orders?
Yeah. Difficulty.
So like a two-dimensional one, three-dimensional one, what?
Sure.
3D switching. Okay. You have to switch in 3D too. Yeah. So maybe this tetrahedron.
Yeah, I love that.
Wait, but I already did it 2 different ways. Can you guys do it the 4 other ways? There's 4 other ways that you can slice this.
Which way is the best? Probably the 2 that he did.
No, not necessarily. If you only had to find 2, then I mean this one, and then just switch z and y. Like instead of slicing it y first, or I guess y first, then z, slice it. It's gonna look exactly the same, but you could switch the order of that. Okay. Yeah, I can do this one. This one's good. Okay, copy. I don't really have any space to do it. Okay, let's look at this and try and slice it 6 ways. The heck just happened? Oh, I was just curious like where it is. Okay, there it is. So this is a good one to kind of see. So assuming that we can get to this picture, that you can figure out what the bounding planes are. Okay, so like this bounding plane in the back is y equals x. This bounding plane right here is z equals y. This bounding plane is x equals 1. And then the bottom one is z equals 0.
Give us those.
I mean, I would give you those. Yeah, I would give you those equations. Sure. Assuming that those are given to you, then let's try and slice this 6 different ways. So what are the 6 different ways? There's dx, dy, dz. There's dx, dz, dy. There's dy, dx, dz. There's dy, dz, dx. And then there's dz, dy, dx, dz, dx, dy. Those are the 6 different ways we can slice it. Let's set up the integral all 6 ways. I think that would be really good practice on kind of visualizing how to do it. For these 2 orders, how do we think about that type of slicing? What does that look like? How do you read dx, dy, dz? What does that mean? You're slicing in the x first, and so the x have to be our bounding surfaces, and so we're going to project into the yz plane, right? So for these 2, we're going to project on the yz plane. And so if you project this guy into the YZ plane, which is this back plane right here, what will it be? It will like, so it's kind of hard to see, but it's going to be this blue triangle face right there, pushed up, like pushing that. And so in the YZ plane, so projection in the YZ plane is going to look like that triangle. And why is that the case? Well, because this triangle, everything else is either parallel to it or like going more in. And so like if you push it, it like the whole solid will be within that triangle. Because the idea is like if this line back here was instead going out like that, then pushing this triangle wouldn't be enough, right? Because it wouldn't project everything. Because there'd be some stuff on there, but because it's coming in, it catches it all. So in the YZ plane, what does that triangle look like? It looks like so 0, 0 is there, and then it contains this point and this point. So 1, 0. So 1, 1, and then it contains this point. And so this is my Y and Z. And so it contains this line right here. And then which side of it is it on? It's going to be on the bottom side, right? Because it contains the point. It contains this point down here. And so this is the region, my projection. What are the bounding surfaces? Bounding surfaces. So they have to be X bounding surfaces. Because we're projecting everything to Y, what are the two X things?
0, X equals 0.
So the tetrahedron line, so there's like a line right here, and the tetrahedron line is on this side of that line. And so as we slice it with X's, one of them, the bottom one is going to be that back plane, and the front one is this blue face, right? Y. And so one of them is X equals Y, and then the other one is X equals. So the bounding surfaces are X equals Y to X equals 1. X equals Y to X equals 1. And now there's two ways that we could slice this, right? One way is I could slice it Y ways first, and then on a particular Y slice, see where Z is going from. Or I can slice it Z Ys first, and then on a particular Z slice, ask where Y is going, right? And so let's do, I don't know, whatever one, it doesn't really matter. So let's do, so bounding surfaces goes from Y to 1, and then it's just 1 dx. And then you want to do dy dz, let's do that one. So where is Y gonna, or sorry, Z is the most outer thing. So Z starts here and goes all the way till the 1, so it has to be constants, 0 to 1. And then on a particular slice, let's pick a particular Z slice. Where is the Y value going from? It's going from Y equals Z to 1. And so it's going from Z to 1. Now to do the other way, to do switching Y and Z is not hard. And so we can do that. It's going to be the integral from, oh, well, let's do the first one. It's still Y to 1 because that bounding surface is still the same, dx. And now we're going to do dz dy. If we do dz dy, we're going to slice it. Where's Y going from? It goes from 0 to 1. Maybe I'll do that in black. So that's still 0 to 1, right? Because I'm slicing like this. They go from 0 to 1. On a particular Y slice, where are we going from? So from like here to here. Where do my Z values go from? They go from 0 and they end at Y. 0 to Y. So that's two ways to do it. We can do this exact same argument for every projection, right? We can do the exact same argument for every projection. And so now let's do, I don't know, let's do the projection in the XY plane. So now let's do projection in the XY plane. And then our bounding surfaces. So if we project this guy into the XY plane, then what are our bounding surfaces going to be? They're going to be between. So they're going to be what type of surfaces? They're going to be blank equals. If we're projecting down into the XY plane, then what variable should our surfaces be? Z. They should be Z. And so Z equals 0 is the bottom one. And then Z equals Y, right? So from Z equals 0 to z equals y. Because we start down here at this surface and then we go until we hit this surface, right? And then what does the projection look like? So in the xy plane, xy, it's kind of, maybe it's kind of an illusion here, but it's helpful to look at these points, right? So we're ignoring the z coordinate, or sorry, this point, this point, this point, and we're ignoring the z coordinate. So it has the point 1, 0, and it has the point 1, 1. And so actually this one's not that hard. This one actually is exactly what you think it is. It contains this point, and then it contains this point. And so it's actually the exact same picture. So it's going to be literally the same picture. So if we slice it so it's 1 dz, let's do dy dx. Let's do that order. Where's z going from? 0 to y. And then I always like to do the outside one first because it's always a constant. Where are x slices going from? 0 to 1. And now on a particular x slice, where's our y going from? 0 to y. That's kind of interesting. And then we can slice it another way. 1 dz, and then now dx, dy. If we do that, it's almost exactly the same, 0 to y, 0 to 1, but then on a particular y slice, where's x going from? Y to 1. And so the fact that all these are the same is kind of interesting, but they are all going to be the same. I hope so.
Yeah.
And so now I can literally copy and paste this picture. And it's almost the exact same thing, except for now we're not going in the XY plane. We're going in the, what plane haven't we done yet? The XZ plane. And so this needs to be X, this needs to be Z. Bounding surfaces are not going to be Z equals, they're going to be Y equals. And so let's look at this picture real quick. If we're projecting into the XZ plane, which is this back plane right here, this one's probably the hardest one to see. But what would that projection look like? It's basically you take this line and collapse it. So you're going to have that line here. And then this line right here will collapse and it makes a triangle. And so it's actually the exact same picture again. So it's literally the exact same picture. The projection is the exact same. So in the XZ plane, it's the exact same projection. But now, where is our Y values going from? So Y goes from, this one's actually, this back plane. Yeah, it's from Z to X. That one is by far the most confusing. It's from Z to X. So it's from Y equals Z to Y equals X. Because Y equals Z is this plane, and then a Y you go until you hit that other back plane. This is that's very hard to see. That's by far the hardest one to see. But that's what it would be. And then the projection is literally the same picture. The projection, all three of them is the same. That's kind of funny. That's not always the case, but in this case it is. Yeah, it's not that case. Yeah, what's up? So on the exam, I'm going to ask you to pick two. I'm going to ask you to pick two.
So we could just be like Y, DZ, and then yeah, DZ, and Y.
I don't know. You pick whatever two you want. Whatever you feel frisky about, Sam. Okay. Also, but let's erase these and figure out what these are going to be. And also these are going to change order. So these all change. These all change. Okay, so now what order we're in? We're in dy, and then you can do, I don't know, dz, dx. So dy goes from z to x, and then our x slices go from 0 to 1, and then on a particular x slice, we go from 0 to z. 0 to z, and then again from z to x, and then on a particular y slice, not 0 to x, it's going to go from, so we sliced it z-wise. And so on a particular, we go from z to 1.
The like second one on the first one
This one?
that you had, one you just,
This one.
that be 0 to Z or 0?
Should be 0 to x. Thank you. 0 to x. Because it's a z value. So on a particular, because we slice it in x. Wait a second. Hold on. Let me listen. Yes, we slice it for x and then pick, and then z goes from 0 to x. Yeah, 0 to x. And then this one is, yeah, from z to 1. Okay. And so this should be dy, dx, dz. So that's all 6 ways. So if you can feel somewhat confident on that, I think that your ability to slice and project is like, that's like a really good example. No, I mean, I'll ask you just to set it up. I will not ask you to integrate them. What's up? Yeah, so there's 6 different ways you can slice it. I'll ask you to do 2. Any 2. You pick your slicing. I should have made you pick 3, but it would have taken too long. Huh? They have to by basically by definition, yeah. They all have to be the same. I guess it's not by it's by Fubini's theorem, but it's just the bounds will change when you change the order or whatever. But you won't have to evaluate it. You just have to set it up. Yeah. And I recommend not evaluating because it's a lot of time. I would just look over, make sure that your projections make sense and that your slicing makes sense.
Yeah. I have an answer.
Yeah, that's what I was gonna say. We should probably do one of those next. Yeah. Your Jacobian equals 0, that's problematic. It means your transformation wasn't 1 to 1. Then you made a bad change of variables. Yeah, you can't, if you're doing an integration problem and you're using a change of variables, your Jacobian cannot equal 0 because that would imply that it's not 1 to 1 and our transformations need to be. So
I love that.
So here's this one is a really good example. We should probably do this one. So this the one that you did? Is this the one you did? Okay, you did A2 as well. Okay. This one is sufficient. So let's do this one. Let's do it. Okay. So we want to integrate this thing where D is bounded by a bunch of random planes. And I'm going to tell you right now, it really doesn't matter what it looks like because I don't care what it looks like. All I notice is that, hey, it's some equation equals a constant. The exact same equation equals a constant. That's going to be one of my variables. That's going to be U. That's U. That has to be U. And then I'm like, oh, look, the exact same thing. That must be V. And oh, look, we did it again. That thing must be W. So please don't mess that part. If you mess that part up, the rest is going to be impossible. And so choose the correct. It's going to be so obvious what the coordinate system needs to be. Yeah. No. It doesn't matter which one you call U, V, or W. You just need to be consistent. So once you pick it, it's fine. But great. Now what do? We need to write that. So U equals X plus 2Y. V is equal to X minus Z. And then W is equal to 2Y minus Z. And then now we have to figure out what X is, what Y is, and what Z is. This is a slightly harder linear system, but not impossible. My gut tells me that, I don't know, actually. I guess you could add these 2 equations to get that. I don't know. Or not add them, but we need to get X and Z. We need to get X, Y, and Z in terms of U, V, and W. That's like the next step. So we need to get X, Y, and Z equal to stuff. I don't know. I guess you could do X equals 2Y minus U. Y equal, oh wait, Y I can get in terms of U. I did this in that, so I'm just trying to isolate stuff. This one tells me, and this one tells me something. This one tells me that z is going to be x minus v.
Is that X correct? Should that be X? Was U minus 2y?
Yeah.
Is it u minus 2y? Oh, whoops, yeah, sorry. U minus 2y, yes, u minus 2y. And then this is telling me that there's some relationship between y and z. I don't know. There's got to be a better way to do this. Yeah, that's what I'm thinking too. So x is u minus 2y, but x is also equal to v plus z. And so I can set those equal to each other. And so, yeah, v plus z equals, I'm like almost so tempted to like write a matrix and just like solve this matrix system to do the linear thing because this is so frustrating to like solving linear systems like this, like we're substituting stuff is so frustrating when I know that there's a better way. But anyways, wait a second. No, not quite. I think 2y I can get in terms of z and w, right? 2y is equal to w plus z. And so I can plug that in right here. And so then v plus z equals u minus, minus 2. No, 2y. No, we have 2y. So minus w plus z. I don't know why that's going to help us. Oh, it will help us. Because then z equals u minus w minus z minus v. Hey, look, there we go. Then you add it, you get 2z equals u minus w minus v. So z equals u minus w minus v over 2. Oh gosh, that was a lot of work. Okay. Now that we have z, we can use that to find x. Because then plugging this, sorry, if this is not, I'm going to say this, the one on the exam is going to be much easier. This part is much harder than the one that I picked. I picked much easier linear system.
This is gonna be the whole exam.
Yeah, this part takes forever.
Yeah.
So then x equals you add v to the other side. And so it's u minus w minus v over 2 plus 2v over 2. And so it's u minus w plus v over 2. And then once I have that, how do I get y? I guess I have z. Yeah. So I could do it in this equation or this equation, either one. Which one do we prefer? Let's just plug it in here. Okay. Actually, let's not plug it in there because that's gonna, we have to subtract it. Let's do the other one. Let's plug this in. Let's plug this in right there. So u, and then bring it down here. So u equals u minus w plus v over 2 plus 2y. And so y equals, oh gosh. Y equals u minus 2u over 2 minus u minus w in parentheses plus v over 2 equals 2y. So then what the hell is that? U plus w minus v over 4 equals y. Holy crap. Okay. Oh, okay, we got it. What the heck is it? U minus w plus v over 2. We need this in order to get the Jacobian. You need to get x, y, and z in terms of u, v, and w in order to get the Jacobian. So this part is definitely the most annoying part.
It's because he has u, but then the subtracting.
I didn't have the same denominator, so I made 2u over 2. So it is u, but then I just multiplied it to yeah. And then I divide by 2 to get 4. All right. If you didn't get to hear, that's okay. Just pretend that this was handed to you. It's not hard. Like the one that I give you will be much easier to get to this point. I promise. It will be like something is something. Plug that in. Then it's like it's gonna be. It'll be easy. Yeah, that one is gonna be something like that. Okay, let's compute the Jacobian. Let's do the Jacobian. The Jacobian is a function of u, v, and w, and it equals the determinant of you take the partial of x with respect to u, w, and v in that order. And so what's our integration? What's the derivative with respect to u? 1/2 with respect to w, with respect to v. 1/2 with respect to w. Negative 1/2. What's the derivative of y? 1/4. Negative 1/4 because it's v, and then w is 1/2. Oh, 1/4 also. Why did I make that 1/2? 1/4. 1/4. And then finally we get 1/2 minus 1/2 minus 1/2. Oof, that Jacobian is gonna suck. Wow, that sucks. Okay. Let's just expand the top row. It's 1/2 times that becomes positive 1/8 plus an 8, so it's a 4th. Minus 1/2, because you have to make the second term negative, like the opposite. And then crossing out that and that, that's minus 1/8. And then minus 1/8 gives us minus a 4th. And then finally minus a 1/2, because that one's just the regular. And then crossing out that and that becomes minus an 8. And that one becomes plus an 8, so 0. Oh, that's actually not that bad. And so that becomes 1/8 plus 1/8, so it's 1/4. So the Jacobian is 1/4. Great. Jacobian's 1/4, so we're ready to rock and roll. So the integral over the region D of, I think it was yz dv instead becomes, now we can integrate with respect to u, v, and w. I don't remember where they go from. It says in the beginning. U goes from, it looks like 1 to 2. V goes from 0 to 2. And then w goes from 0 to 3. And then we need to plug in what y and z are. So y is u plus w minus v over 4 times z, which is u minus w minus v over 2, times the Jacobian of 1/4, and then du, dv, dw. And that's the final answer. I'm not gonna do that. No, that's a waste of my time. If you do, it's gonna be much simpler than that. That's really hard. That one sucks. The only integrals I ask you to do are all relatively easy. Because it was only y and z. Because the function was just y and z, and so I replaced y and z. But yeah, you have to just plug in everything in so that it's just in u, v, and w. Yep. It's doable. No, the Jacobian one's super doable. It's fun, it's doable, not bad. I think it's. What else do we do? What time is it? 3:15. Yeah. Yeah, we can. Let's do a spherical coordinate. There's actually a center mass one with spherical coordinates that would maybe be good to do.
Yeah.
Yeah, I don't know, maybe.
I did that too, probably. He wouldn't give us the easy
Um, let's do this variable density solid. Find the coordinates of the center mass of the following. This one uses spherical coordinates. So it's the upper half ball. So rho goes between 0 and 16, phi is between 0 and pi over 2, and theta goes between 0 and 2 pi. And they tell us the density function is 1 plus rho over 4. So because of symmetry, that's gonna be said a lot with these things. Because of the symmetry, we get that, so I don't know if this is like X. We have like this upper, it's like a dome, right? It makes a dome. That's not a dome. That's really bad, but hopefully you understand what it is. It's a dome. And because the density only depends on distance from the origin, right? Because that's what rho is. Then we can, this always is the thing. So then where's the center mass gonna lie? On the z-axis, right? Because there's the same amount of mass around it, and so it has to lie on the z-axis. So x bar equals y bar equals 0 by symmetry. And so we need to compute z bar. So we need z bar. Z bar is you integrate over the region D, the density function, z times the density function, z times f of rho v theta times, it's going to be the fudge factor rho squared. So I don't know why I'm already I'm just going to write dv. I don't want to actually write it yet. Let's just write dv. dv over, and then we have to do the mass. The mass is just the integral of the density function. d dv d. Okay. Let's just do the mass first. The mass is actually, and is it okay if I just like not go all the way? I don't want to go all the way. The mass, let's just set it up and then we'll see how far I want to get. Okay, sounds fair. The mass, so because we're integrating this with spherical coordinates and these are all constants, it's going to go, theta goes from 0 to 2 pi, rho goes from 0 to pi over 2, and then, or sorry, phi, and then rho goes from 0 to 16. And then what am I integrating? Well, this is the density function, so I have to integrate that. And it's already in spherical coordinates for me, so that's great. And then I need to multiply, I need to change dv, right? gv needs to be changed, and so I have to multiply by the fudge factor. Rho squared sine phi. D rho, d phi, d theta. Oh, I don't like that. It's not a U sub. It's because you're integrating with respect to rho. And so it's not that it's hard, it's just not that it's nice. Oh, okay. It's rho squared sine phi plus rho to the third over fourth sine phi. And then I'm integrating with respect to 0 to 16 d rho. And then, the rest. I just distributed. Okay. Now I integrate with respect to rho. You get rho cubed over 3 sine rho plus rho to the fourth over 16 sine rho. Sine phi. I keep saying rho and phi. Same, sorry. 0 to 16. That's going to be not super nice, but we can do it. 16 cubed over 3 minus, no, sorry, plus 16 to the fourth over 16. Hey, that's just 16 to the third. That times sine of phi. I'm integrating that from 0 to pi over 2. And then times 2 pi. So there's a lot of, this is really, really sloppy, but that's, I'll just say it leads to 2 pi times that. And then that we can integrate, right? That's actually not that hard to integrate. What's the antiderivative of sine of phi? It's negative cosine. So it becomes 2 pi times whatever number this is, 16 thirds over 3 plus 16 thirds. And then times negative cosine of phi evaluated from 0 to pi over 2. If you plug in pi over 2, that's actually 0. If you plug in 0, it's 1. And so it actually just equals 2 pi times 16 to the third over 3 plus 16 to the third. So that's the mass. That's not bad. For this one, we have to change z into polar coordinates. So I'm just going to set it up and not actually do it. But the moment with respect to the xy is going to be this integral from 0 to 2 pi, because that's theta, 0 to pi over 2, because that's phi, 0 to 16. And then I need to change z into spherical coordinates. What is z in spherical coordinates? It's on my note card. It's rho cosine phi. Rho cosine phi is what it is. And then times the density function, which is 1 plus rho squared over 4, and then times the fudge factor, which is rho squared sine phi. So you can tell that this is going to be much, much more horrific.
Would the one on the exam be this horrific?
No, no. And if it is, then you just have to set it up. I would never ask you to integrate something this hard. Not all the way. Whoops. Except for on the online homework. But that you have infinite time and you have Desmos, and so I don't care. But on an exam, your resources are much more limited.
This is easy.
Yeah, to anti-differentiate that, you have to use U substitution because you have to let U equal. I guess it's not the end of the world, but it's not the beginning of the world either. So, yeah. It's not my favorite, but it is my least favorite. All right, hold on. I want to see how my teams are doing. Probably not great. Mhm.
It's still winning.
Oregon's winning? Okay, good.
I did like 3 months ago.
Okay. Okay. Hey, let's go.
Now we're going.
Oh, let's go Nevada. That's what I'm talking about. Let's go. Oh, I'm recording this right now. Oregon crushed it. Let's go. Guys, I'm looking really good. The only thing I didn't pick was Michigan State, which, yeah, it's okay. Not everyone's perfect, right?
You're not going to